Piezo Haptics offers unparalleled levels of flexibility when it comes to integrate high-definition tactile feedback in your next device. With our cab drive Piezo Haptic drivers exclusive pressure sensing feature and off-the-shelf piezo actuators like TDK Corporation Power App lineup, you can easily integrate better haptics to your new product design and improve the user experience. In this video, you will learn how to maximize feedback force and the common challenges you may face while integrating piezo haptics to replace buttons.
Piezo actuators are perfect to generate localized, high-definition tactile effects. Since you don't need a mass to replace mechanical buttons with piezoelectric haptics, you only need to focus on treating the frame's wall rigidity to optimize the tactile feedback quality, protect the actuator from excessive force, the actuator's output frequency bandwidth to stimulate the finger's mechanoreceptors. The frame's wall rigidity will have a major impact on the piezo actuator's haptic feedback quality. The actuator has two symbols that generate opposing force when voltage is applied to the actuator. This is why the actuator needs to be installed between two walls, one inside the frame and one on the outside. Based on Newton's third law of motion, the less rigid of the two walls will deform when force is simultaneously applied on both of them. Here are three situations you may face while evaluating the wall's rigidity. First situation, the two walls are too rigid for the actuator. In this case, the user won't be able to feel the force from the actuator, since there will be no displacement and there's a high chance of failure from the actuator if the walls don't deform with it. Second situation, the inside wall is less rigid than the outside wall. In this case, the feedback will be felt from the inside of the device because the inside wall will deform under the actuator's force instead of the outside wall. This isn't what we're trying to accomplish with piezohaptic buttons. Third situation, outside wall is less rigid than the inside wall. In this case, the feedback is felt from the outside because the less rigid the outside is, the more freely the actuator can move and better the tactile feedback is. This is exactly what we're looking for. Easy, right? Your outside wall needs to be less rigid in order to achieve the best haptic feedback. Well, not so fast. If your outside wall is too soft, you may face durability problems. Since the piezo actuator is bonded against the outside wall, it can be subject to absorb excessive force from various sources if the outside wall is too thin or not rigid enough. Your device may fail drop test if the outside wall is too thin. You need to concentrate on finding the right balance between protection and feedback quality. Using piezo actuators to replace mechanical buttons doesn't need to involve a mass. Therefore, it's easier to integrate. Since you don't have to find a mass natural resonance and because piezo actuators have a wide frequency bandwidth, you may be tempted to use the highest frequency the actuator can use in order to generate the strongest feedback possible. Beware, because the optimal sensitivity of mechanoreceptors in your fingertips is between 200 and 300 Hz. You need to operate the actuator in this frequency bandwidth to achieve the best tactile effects. The wall's rigidity can affect that optimal frequency, so you may need to experiment and find the best feeling. Thanks to the wide frequency bandwidth of piezoelectric actuators, you could even let the user choose his preference within the bandwidth via software. You aren't limited by piezohaptic hardware like you would with an ERM or an LRA.
We share with you the basic mechanical concepts behind replacing mechanical buttons with piezo haptics. Our engineering team has developed multiple advanced concepts to achieve the best levels of performance and protection. Don't hesitate to reach us at info@boreas.ca to kickstart your next project with help from both our electrical and mechanical engineering team.